Hello everybody, this is Hanson. So I want to create this playlist for people who wants to pass the SOAP exam and want to become an actuary in the future. Um, and the whole playlist is going to be solving questions. So I'm going to assume all my audiences knows about probability already and basically everything in the manual. And then we're just going to solve some questions together. So usually I would like to randomly select 5 questions per packet, and for each question, I'm going to give you guys 5 minutes. So I think I'm going to let you guys time yourself to do one question, and and then I'll talk about it. So that's pretty much the plan for today's video. Okay, so for today I have 5 questions to show you guys. Question 446, question 146, question 11, question 185, and question 158. So let's go ahead and get started on the first question. So please pause the video and probably spend 5 minutes on this and see if you guys can figure out yourself, and I'll talk about it. Okay, so let's get started. So this problem is basically about the joint probability. Okay, so you guys may wonder, well, why is that? Well, the reason is that whenever we see some tables like this where two categories are present, and also we have some um, probabilities which corresponds to um, the two different conditions, then it's probably going to be some joint probability. So we know that the whole situation was separated into two categories. The first one is the morning. The second one is the afternoon. And the question told us the expected length of the assigned afternoon is 11 miles. So that's something we probably want to use to find x and y. So since the question gave us some information about the afternoon, maybe we need to do some arrangement to the original joint probability distribution, and maybe try to make it the distribution only for the afternoon so that we can find x and y. So that would be the plan. We focus on the afternoon. So if we only focus on the afternoon, which means that we don't really make distinctions between so what's going on with the morning. We just treat them to be the same. So there are 3 cases. So 0, 5, and 30. And for the rest, I just combine these probabilities together. So for the 0 case, 0 plus 0 plus y equals to y. For the 5 case, 2x plus 2x plus 0 equals to 4x. For the 30 case, 3x plus 0 plus 0 equals to 3x. So this is the probability distribution for just the afternoon. Now we know that the expected length, let's maybe call the afternoon the random variable x and morning capital Y. So they're both capital. And the expected value of x, the question says that this equals to 11. And also we can use the expectation formula to get 0 times y plus 5 times 4x plus 30 times 3x. And the good news is that the y is eliminated. So if the coefficient of y is a non-zero number, this problem, it's probably going to be, there's more than one unique answer, or it is unsolvable. And because we have a 0 here, it's very easy for us to find the x. So this is going to be 20x plus 90x, which is a pretty decent number because 20 plus 90 equals to 110. So that will give us x equals to 0.1. So x equals 0.1 means that this is 0.2, 0.2, 0.3. And because the sum of probabilities must add up to be 1, this means that y has to be equal to 1 minus 0.2 minus 0.2 minus 0.3, which is exactly 0.3. So y equals to 0.3. Maybe I'll also write it here. Very nice. Now we solve the variables and we understand the details of this joint probability distribution. And the question asks us to calculate the variance of the length of the afternoon route. And again, we're working with the afternoon route. And there are exactly two ways to find the variance. The first way, which I'm going to denote it by method 1, is to use the variance formula. Directly came from the definition. So the variance is defined. So we're finding the variance of x. So the variance of x is defined to be the expectation of x minus the mean. And we need to square the difference. Okay, and this is just the definition. So, and since we know the mean equals to 11, we can probably just plug in the value. So let's see. So the zero case, the corresponding probability is y, which is 0.3 times, so x equals to 0 minus the expected value squared. And the 5 case, the corresponding probability is 0.4. 0.4 times 5 minus 11 squared. Okay, and then I have the 30 case, which is 0.3 times 30 minus 11 squared. Okay, so let's go ahead and use a calculator to find the value. And let me take out my calculator. Okay, so I got 159 as the answer. So the correct answer should be A. And since we're practicing, let's also do the second method, which is the shortcut formula. And I'll actually recommend you guys to use the method 2, since sometimes it's easier. So the shortcut formula for the variance is the expected value of x squared minus the we find the expected value of x first and square it. So this is the notation I like to stand for the square of the expected value. Okay, so and by the way, this shortcut formula came directly from the previous formula, but I'm not gonna prove them here, since I already assume you guys know how to prove it. If you guys don't know about that, please go to the study manual, and in the manual they will have the proof of this. So we're not gonna spend too much time on the proofs here. So actually let's find ex squared first. So this is simply going to be 0 squared times 0.3 plus 5 squared times 0.4. So 0.2 times plus 0.2 equals to 0.4. And finally, the 30 squared plus 0.3. I mean, times 0.3. And you guys should get the same answer of 159. Oh, sorry, not 159 actually. Maybe use a calculator. Oh, actually 180. Okay, and then I need to find the square of the expected value, which is just 11 squared. 121. Find the difference. 280 minus 121 equals to exactly the same answer. 159. Okay, so that's the end with the first problem. So um, let's go ahead and go to the next one. Question 146. So again, let's spend 5 minutes, pause the video, time yourself, and see if you guys can figure this out. Okay, so let's talk about it. So we have, whenever we see a given here, and we want to basically find a probability given something, something, something. This is usually about the conditional probability. Okay, and what is a conditional probability? Well, it's simply the probability of something happening given something happens. And when we try to do that, we need to shift our view from globally to um, the place where something happens. So basically the formula of P A given B, let's review a bit here, equals to the below is P B and the above is P A and B. So this is the formula for the conditional probability. If some of you are not familiar with this formula, then probably check the manual, go over the manual again, and they are all in the manual. So we want to find the probability that the machine has the third malfunction on the fifth day, given that the machine has not had the third malfunctions in the first 3 days. So basically, and also we know that the probability of malfunction on any given day is 0.4. So that's just some probability there. And the mutually independent is the key here. Because if there are some covariance between the events, we cannot multiply the probabilities together to get their end. So the mutually independent is the key here. So basically, let's actually find the probability of the machine had its third malfunction on the fifth day, and also it had not it has not had the three malfunctions in the first 3 days. And this is basically equivalent to the first condition because if it has the third malfunction on the fifth day, there's no way that the machine has the three malfunctions in the first 3 days. So let's list all the possibilities. So for day 1, day 2, day 3, day 4, day 5, and we know there's going to be one malfunction on the fifth day. Well, then I'm basically choosing for the first 4 blanks, I need to choose 2 days where the machine has one malfunction. And don't forget, one day only has exactly one malfunction. So we don't care about the case when there are 2 malfunctions in a day, so just one malfunction. Okay, so it's basically a 4 choose 2 situation, which gives us 6 possibilities. So 1, 1, 0, 0, 1. I can do 1, 0, 1, 0, 1. I can do 1, 0, 0, 1, 1. That's also one possibility. I can do 0, 1, 0, 1, 1. That's also one possibility. And finally 0, 0, 1, 1, 1. Oh, actually there's supposed to be one more. Oh, I forgot. There should be one more, which is right here. So 0, 1, 1, 0, 1. Okay, so very nice. So there are 6 possibilities. And what's their probability? Well, for all the cases, we know that since, again, they are mutually independent, I can just multiply the probabilities of each day together. So since the probability of malfunction on any given day equals to 0.4, and there are exactly 3 days of malfunction, then it's going to be the probability for each of the case will be 0.4 cubed times 0.6. So this is basically the probability of some any given day which there's no any malfunction, and there are 2 days of that. And since the probabilities are equal, and there are exactly 6 of them, I can just multiply this by 6 and give us the answer of, let me use my calculator. 0.13824. Okay, and now if you guys think that option B is the correct answer, then that's a trap because we only found the probability of P, A, and B. And we don't necessarily look at this probability globally. This is actually just the probability based on what B happens. Or maybe I need to clarify that a little bit because I think that was wrong. So we want to find the probability given B already happened. So I need to divide this probability by the probability of the machine has not had 3 malfunctions in the first 3 days. And this is hard to find, honestly, because that requires a lot of combinatorics. So instead, maybe we should use a shortcut, which is to find its complement first, and you just use 1 subtracted the complement from the total probability of 1. So its complement, it's just going to be the machine has 3 malfunctions in the first 3 days. And you see that probability, it's easier to find. So since, again, the probabilities are mutually independent, the probability of the machine has 3 malfunctions in the first 3 days is exactly 0.4 cube. And its complement is just going to be 1 minus that. And let me use my calculator to do that. 0.936. So that's the probability of B here. Okay, and now we can just take the fraction and see what's going to be the final answer. And this is going to be 0.1477 as the answer. And the correct answer should be C. Okay, so basically this problem is testing 2 things. The first thing is the conditional probability formula. And the second thing is a little bit of combinatorics. So we're basically listing all the possibilities here. Okay, so let's go ahead and go to the next question. So again, pause the video, spend 5 minutes on this, and see if you guys can figure this out. Okay, so let's talk about the question. So question 11, it's basically about the probability basics, I would say. Probability basics. Okay, so we do have a lot of options here. We have so basically the 2 categories are blood pressure and heartbeat. Abnormalities in their patients. And for blood pressures, it can be, high, low, or just normal, which I'm going to mark them BH, which means that the blood pressure is high, and BL, which is the low blood pressure, and BN, normal blood pressure. And for their heartbeats, there are 2 options. It can be regular or irregular, which I'm going to mark as RH for regular and IH for irregular heartbeats. Okay, so let's see. The probability of high blood pressure, so the probability of BH equals to 0.14. The probability of BL equals to 0.22. The probability of IH equals to 0.15. And the next 2 conditions are interesting because they are in forms of conditional probabilities. So of those, usually stands for some conditions. So the this is the PBH given IH. Okay, that equals to 1/3. And so irregular heartbeat. So irregular heartbeat is exactly IH given normal blood pressure. So PN equals to 1/8. Okay, so now the first thing I want to do for this problem is that I want to break the conditional probabilities into by the formulas we know, because we never know what these stands for by just looking at the form. So we can immediately do some arrangements right now. So um, the bottom will be just PIH, and this is going to be PBH and IH for the numerator. This equals to 1/3, and PBN, and this is PIH and BN. This equals to 1/8. Okay, so now what's our goal? Our goal is to find a portion of the patient selected who has a regular heartbeat and low blood pressure. So we want to find P. So regular heartbeat will be RH and low blood pressure BL. So if I can find this, we are happy. We can share. And how do I do that? Well, the first things I notice is that I do know about IH. So that's something we are happy about. So maybe I can put this towards the end. Okay, so we know about IH. IH equals to 0.15. So I can immediately change this to 0.15. And I can multiply 0.15 on both sides to make things easier. And this is going to be I will have to take out my calculator. Okay, 0.05 for the n for this. And let's see, what can I do here? Well, I also know about Bn. So what do I know about Bn? So let's see. Bn, it's basically, maybe let's make it so the probability of B, the big category, and I want to get rid of all the possibility which doesn't all the other possibilities. So PB minus, so I want to get rid of the oh, actually, what was I doing? I didn't mean PB. So it's just the total probability minus all the others. So PH and minus PL. I mean BL. And that's the BN, because all the patients are categorized into so in conditions of the blood pressures, there are only 3 kinds. So this is 1 minus 0.14 minus 0.22. Okay, and that equals to, I think, 0.64. So in fact, I can immediately change this to 0.64. Okay. And let's do some multiplication, and P of IH and BN, it's going to be, so multiply 0.64 on both sides. And this is going to be 0.08. Nice. So again, our goal is to find RH and BL. So we need to again try to do something and do that and find that. And one way to think about this is that instead of finding RH and BL first, maybe I can find the PIH and BL. If I can do that, that's going to help us find RH and BL. So let's use this approach. So IHBL, it's simply that out of all the IHs, I want to minus all the possibilities which it is not BL. So IH and BN minus PIH and BH. And the reason I do that is that I know about them. They're right here. So, and also I know about the probability of IH. So this is going to be 0.15 minus 0.05 minus 0.08. Okay. Maybe I should swap the two because I don't want anybody to be confused. But you know, um, that's the correct approach, and I'm getting 0.02. Okay, and now I just need to find P, R, H, and BL, which is just going to be uh, PBL minus PBL and IH. And this is simply going to be 0.22 minus 0.02, which is 0.2. And the answer is A. Oh, sorry, I mean E. Because there's a percentage here. Okay, so this is how we do question 11. Let's go ahead and jump to the next one. So again, let's spend 5 minutes on this and see if you guys can figure out. Pause the video. Okay, so this is a pure combinatorics problem. Combinatorics. Okay, so basically, so for this one, there are 7 candidates here, and I'm always choosing 4. And out of the 4, I want to try to um, I want to switch the chair so that there will be no repetition, right? So basically, this is going to be 7 choose 4 times 4 choose 1. And we don't necessarily care about the secretary here because we only focus on the individuals and the chair. So basically, um, if the secretary repeats, we don't worry that much. Okay, and this is simply going to be maybe let me write the combinatorics formulas as well. So basically, A choose B, it's equal to A factorial and below B factorial and A minus B factorial. So this is like a good way of doing this. And also on the SOA exams, since you guys are allowed to bring some calculators, you may also use the probability function um, to use your calculator to do that as well. Okay, so I'm not gonna do that. I'll just go ahead and compute for this. So 7 factorial, maybe I'll do that. So 4 factorial, 3 factorial times, so 4 choose 1. So anything choose 1 is just that thing. Now I'm just going to use a calculator to be honest. So I'm going to use the probability function. Hmm. Okay, so I'm getting 140, and that's the answer. Okay, so that was a quick one. Let's go ahead and jump to the next question. And I think this is the last question. Okay, so let's go ahead and think about and do this question together. So this is about Poisson distribution. And if you don't know Poisson distributions, this video is probably not the best for you. I will highly recommend you go over the manual first. So this is in the manual. History. Personally, my spelling is really bad. So Poisson distribution. I forgot this. Okay, so Poisson distribution. So to understand how Poisson works, we need to understand the how what its equation is. So for a Poisson distribution, so it's usually studying for some discrete case where p of a random variable equals to some number. And this is defined to be e to the power of negative rho times rho to the power of k, and all over k factorial. So basically, k, it's all non-negative integers. So 0, 1, 2, 3. Okay, and usually we want rho to be positive. And since I'm talking about Poisson distribution, let's also cover its property. So this can be proved. I think the proving is not part of the the exam, but if you guys spend some time and do some proof, you guys will find some surprising property about Poisson. Is that the expectation equals to its variance, and they will equal to rho. And again, we're not gonna prove it here, and also the exam won't test you how to prove them. So uh, but I would still recommend that you guys look at the proofs of this so that you guys can memorize it better. Okay, so basically these are all the concepts we need to know in order to solve this question. Oh, actually, there's one more. Maybe I'm gonna write it as a theorem. So the sum of prosums, the sum of prosums. Maybe I spelled possum wrong. There shouldn't be an I. Okay, the sum of Poisson Poisson distributions, it's also Poisson. And um, so basically, um, how to prove this theorem, it's very simple. So we basically, so I'm going to give you a little intro, and you guys should, if you want to complete the proof, feel free to do so. So basically, I can have P1, P2, Pn to be possums, and you actually add them. So basically, you add them, and then you see you want to see what happens, and eventually there will be a way that you can collect some terms and write everything in forms of this. And I think that the multiplication will basically make the exponent together, and basically we're gonna add a lot of rows here, and the bottom is not gonna change. It's also going to be some sort of factorial, and same with the components here. So you actually add these things together and see what happens. Rearrange something, and you'll get another Poisson distribution. So I'm not gonna talk about the proofs here. But you guys should be able to prove it on your own. Okay, so let's go back to the question. That was the all the concepts you guys need to know. And now let's see. So the number of days an employee is sick each month is multiplied by Poisson distribution with the mean 1. So basically we know that mean is 1 and the variance is 1, rho is 1. We get the distribution. And the number of sick days are in different months are mutually independent. So the independent is the key here. So actually I forgot. I need to say that the sum of independent possums is a possum. Because if there are some relations, then probably we need to be more careful about it. So independent possums, it's also possums. Okay, so we want to calculate the probability that an employee is sick more than 2 days in a 3-month period. So notice that this is a 3-month period. Okay, so let's see. We want to let's get our variables together. So let's use x to represent the probability. So the number of times maybe number of sick times in a month. And we also know that x, it's multiplied by Poisson. With the mean 1. Okay, and now let's invent another random variable, which is the amount of sick times. Sick times in 3 months. And you know, this is simply going to be x plus x plus x, or you know, 3x. Because for each of the months, the number of sick time is multiplied by x. Okay. And because of the theorem, we know y also follows Poisson. Okay. So notice that y it's also follow Poisson, but we don't know about the mean, so we need to probably do some probabilities and figure out the expectations of y. So we know that the expectations of y equals to the expectation of 3x, and because of the property of expectation, I can get the coefficient out, which is 3 times 1, which is 3. So we know what should I fill in the question mark. So y is multiplied by the Poisson with the mean 3. Okay, and now the rest is easy. We want to find the probability that y is greater than y is greater than 2. Yes. So the probability that y is greater than 2, we don't like this super much, because if I do that, what will happen? I need to find the probability of y equals to 3 plus the probability of y equals to 4 plus blah blah blah, blah until the infinity, and which is doable, but you know there are easier ways, which is to find the complement and subtract it from 1. So y equals to 0 minus y equals to 1, and y equals to 2, which is y. So let's go ahead and go back. So this equation needs to be memorized, or we're not able to do any Poisson distributions. So x equals to 0. I mean y equals to 0 is going to be, let's go ahead and write them down. So maybe e to the power of negative 3 times 3 to the power of 0 over 0 factorial minus e to the power of 3 times 3 to the power of 1 and 1 factorial and plus e to the power of negative 3 times 3 to the power of 2 over 2 factorial. I mean, should be minus here. Okay, so these, just use a calculator to handle it. Um, so let me see. The answer I got is 0.577. Let's see if that's in the options, and yes, that's in the options. Okay, very nice. So I think this is all the practice we have today, and thank you very much for watching this video. I will see you in the next one.